Hello and welcome to Empowered Learning. This video will be the first video in the video series on non-homogeneous second-order linear ordinary differential equations and solving these types of equations using the method of undetermined coefficients. So this part one video is going to mostly cover the theory and the strategy behind doing method of undetermined coefficients with these types of ordinary differential equations. The part two video will go over examples. So if you're more interested in just looking at the examples because you already know the theory or you're not really interested in knowing the theory, then of course you want to go to the part two video. However, I do encourage you to watch this particular video because knowing the why and the how behind this particular method of solving these non-homogeneous equations actually does help whenever you go study other types of methods. For instance, the variation of parameters method for solving these same non-homogeneous second order linear ODEs gives you better insight into knowing why and how we actually solve those as well. So like I said, in this video, we are going to talk about the why and the how behind this method of undetermined coefficients. But the first thing that we need to do is to actually define what do we mean when we say a non-homogeneous second order linear ordinary differential equation. So let's start with that. So should already be familiar here with the general form of the equation that I'm writing now. And this is a second order linear homogeneous equation. And of course, we're looking at it where all of the constants A, B, and C, or all of the coefficients are constants. So when we talk about a non-homogeneous second order linear ordinary differential equation, then we know that this right-hand side here is just going to be some function. And it'll be a function of x, or we may make it a function of t. Really doesn't matter. We just know that it is some function, okay? So in short here, we're just going to put that is going to be a function g. And we'll leave it to the problem to distinguish in between what the independent variable will be. All right, so we'll just put a g there. Now, before we get into our discussion about solving non-homogeneous second order linear ODEs, I want to remind you of some things about the second order linear homogeneous equations that knowledge that we're going to be carrying with us here. Okay, so we know that in this point that we've sort of built the knowledge for solving these second order linear homogeneous equations that I've talked about. Okay. We also know that the solutions or general solutions that we get to those equations here are mainly based upon the characteristic equation, which we know is just a quadratic equation. And depending upon what the roots are, that depends upon what our general solutions look like. And so I'm going to go over a quick review of what that looks like here because it actually helps us in trying to learn this method of undetermined coefficients method. So for those of you that are following along in the videos I'm recording for this particular subject, you'll remember here that I had a summary of the cases 1 through 3 for the second order linear homogeneous equations where all the constant coefficients, we have all constant coefficients here. And we knew that in general that our general solution to these ODEs are of this type of e raised to the rx. And of course, the roots would tell us what the solutions look like. Case 1, where we had two real distinct solutions, would just end up being a linear combination of the two different exponential functions. In case 2, since we only had one actual distinct solution, we knew that this particular root had multiplicity 2, and that forced us to be able to do reduction of order to find the other solution. And the other fundamental solution was x times e raised to the rx after doing reduction of order. So we know that this is what our general solution looks like in a case 2 situation. And then, of course, for case 3, we had the complex conjugates. So, of course, in general, we had the solution of y is equal to e raised to the lambda plus or minus omega I. But we knew here that having it in complex form wasn't real advantageous for us. So we had to find a linear combination of it just using real value functions. And we see that we found out that cosine and sine was actually cosine and sine times this exponential here was actually functions that were part of the basis of solutions for it. So, and notice that with all 3 of these, we are assuming that we can use the principle of superposition to take those fundamental solutions or basis solutions of our differential equation and say, hey, as long as I have the basis functions, then I can do any linear combination of them to be able to get other solutions to that particular differential equations. And so by using superposition, we actually have a family of solutions that would work for a particular differential equation. And so that is what we learned when we talked about that. Now, the thing that is important to know here, and part of the reason why I'm going over this review, is that the one thing that we are going to see whenever we talk about the method of undetermined coefficients, or the reason why we even do method of undetermined coefficients in the first place, is because we're not going to be able to assume by the superposition principle that if we have a basis of functions for this non-homogeneous differential equation, that we can actually come up with a linear combination of those solutions. So we won't be able to do that. And so that's one of the main things that I want to show you here. I actually want to go and demonstrate why that is. And so in that, I think in you seeing it, you'll actually intuitively start to understand the actual form for a suitable solution for these types of equations that we're going to study. You'll understand why we have that form. All right, so back to non-homogeneous second order linear equations. So like I said before, it turns out that superposition principle in this application of non-homogeneous equations does not look exactly the same as it does for its homogeneous counterpart. So what I'm saying is that superposition principle is not going to work in the same exact way as it did for the equation type that I just reviewed. The primary issue is that to find a suitable solution for this non-homogeneous second order linear ODE, we need to find a suitable solution for that first, okay? And so this suitable solution is going to end up taking this form. And so what this form is it is a homogeneous solution, which that is the solution types that we just got through reviewing, plus a particular solution. And we don't know what that is. So at best, we're going to have to guess. And so that's one of the reasons why we have what's called the method of undetermined coefficients, because we have to make a guess on what we think the particular solution will look like. And then afterwards, try some things out to make sure everything works. Okay. So that's really the main idea here. And the goal of this video is to, one, show you how we actually come up with the fact that y of x is going to be a sum of a particular solution and a homogeneous solution, as well as go over the basic strategy for how to do method of undetermined coefficients. And again, the second video will just be a bunch of examples. All right, so now I'm going to methodically go through this portion of the notes that I have here, just to make sure that you understand why it is that this is actually a suitable solution for these types of equations. Okay, so we start off by supposing that we have two particular solutions, and we're going to call them y sub a and y sub b. Okay, And when we say particular solutions, we just mean that we have solutions where we don't have any arbitrary constants like the C1s and C2s and C3s that we've seen in the second order linear ODEs, as well as if you've watched some of my other videos, the Cauchy-Eulers, all that. We don't have any undetermined coefficients, undetermined constants in those functions. Okay, so instead of having something like, let's say, y is equal to c1 e raised to the 3x plus c2 e raised to the 5x, something like that, we would know exactly what c1 and c2 were. Okay, so here we would say, all right, let c2 be 2, c1 be 2, let c2 be like -3. So something like that. All right, so understanding that we have two particular solutions that we are assuming that satisfy this particular equation here. And of course, we know that A, B, and C are all going to be constants, and this G here is not going to be 0. So now we're assuming that these two functions are solutions of the non-homogeneous counterpart of the equations that we have been working with. Okay. Now, this next sentence here is assuming that we can use superposition just like how we did whenever G here was equal to 0. Okay. In other words, when we had second order linear homogeneous equations, we're going to assume by superposition principle that I can take my two particular solutions here and do linear combinations of them, and I should, and I've underlined should here, because we know it's not going to end up being that, but we're acting as if we don't know that. But it should also, this result here should also be a solution to our non-homogeneous second order linear ODE. Okay, so we make these assumptions. Hey, these satisfy this equation here, where of course this g of x is not equal to 0. And we assume that, of course, linear combinations of these will also be solutions as well. So if that's the case, we can actually find the first and second derivative of what we're proposing the general solution would be, and it should work out. Okay. So we start off here by taking the first derivative of our function y of x. So we see we do that with no problem. We also do the second derivative as well. Once we're done with that, what we need to do is just take this general solution here and its first and second derivatives and just plug it in to our original ODE. So when we do that, you see here we have the y double prime. Here we have the y prime. And here we have the original function, or what we assume the solution would be, which would be a linear combination of y sub a and y sub b. So we go ahead and in this step, we write that all in. And then in the next step, what we do is rearrange a bit. And if you notice, what I've done is I've taken all terms that have C1 in them, and I've grouped them together, all terms with C2, and I've grouped them together. Okay. Now, notice that when I do that, in each of my groupings here, I notice that I see something familiar. And what I'm seeing familiar is that that looks exactly like the left-hand side of the original ODE that I was going to deal with. And of course, I know that if that's the case, and these are particular solutions here, y of a and y of b that satisfy that equation that I'm trying to deal with, then I know that both of these expressions in here have to equal g of x. Okay, and so that is what I'm stating right here. So now that I know that both of those have to equal g of x, then of course all this is g of x, all this is g of x. So I just have c1 times g of x plus c2 times g of x, which ends up being g of x times the sum of c1 and c2. And of course, what that tells me is that c1 plus c2 must equal 1. Okay. Now, if you look at this, you say, okay, well, that's great. You give me a value of C1. I can give you a value of C2 based upon that. But what we need to realize here is that because I have this condition, meaning that based upon what value of C1 I have to pick a specific value C2 that's really going to be 1 minus whatever C1 is. That's actually violating the superposition principle. Because remember, the superposition principle says that if I have y sub A and y sub B as solutions to my ODE, then it does not matter what C1 and what C2 are. I should always be able to come up with another solution to my ODE. Well, this says, well, as long as this particular constant here is 1 minus C1, you're good to go. If it's anything other than that, then it's not going to work. And of course, again, that violates the superposition principle. And so in all this blue writing that you see here, that's essentially what it is that I'm saying. Okay. So I'm going to go ahead and skip that. So now that we know that the superposition principle as we know it for second order linear homogeneous equations does not work for this non-homogeneous case, then we need to make a couple of observations, and then from that try to figure out, well, what would work. Okay. So the first thing that we realize here from basically seeing superposition fail is that there is not going to be a simple set of two linearly independent functions that will create a fundamental set of solutions, or aka a basis of solutions for our non-homogeneous ODEs by way of the superposition principle. Okay, so we actually saw it. So the second thing is that we know that there are specific combinations of C1 and C2 that will be a solution to our second order non-homogeneous solution. And again, we saw that because C1 plus C2 has to equal 1, if I wanted to come here and say C1 times y sub A, then of course this constant here would have to be 1 minus C1 in order for that to work. Okay? And again, just because that's the case, that doesn't mean that superposition in the way that we've defined it for the homogeneous equations is actually working. So we know that it's not. Now, if we take points A and B and put them together here, we'll see that because C1 plus C2 has to equal 1, again, that means C2 is going to be 1 minus C1. We also know that if I was to go ahead and plug that in like how I've been doing earlier, then we know that this is what our general solution to this non-homogeneous equation would look like for a given value of C1 here. Now, if I rearrange some things, notice that here I have a constant, which is indeed arbitrary, times the difference in between these two particular solutions plus this value of 1. And of course, we know 1 is just C1 plus C2 here, okay? Now, what this is telling us is that, number one, if what it is that we're trying to do, which is find a general solution for the non-homogeneous equation, second order differential equation, if we're going to be able to find a general solution for it, the one things that we're going to have to consider is that that solution is going to look like a constant times the difference in between our two particular solutions that we said that we had, plus another constant, and that constant will always have to be 1. So now, considering what we have observed here, again, we note that if we knew what our particular solution y sub A and y sub B actually were, then the difference of these two particular solutions of our non-homogeneous ODE in question would form a function that could serve as a basis of solutions for this second order linear homogeneous equation. So what we're going to do is assume that's just that. So we're going to say, hey, let's take the difference in these two particular solutions that we're saying that actually satisfy our second order linear non-homogeneous equation. And again, we're going to assume that A, B, and C are constants, and that g of x could be any function in this case, including 0. Okay, so we're leaving it wide open now because we're making some new assumptions here, and we need to see, all right, if we put ourselves in the box of if the difference of those two particular solutions is actually a solution, then how's everything else going to fall out? So that's why we're kind of keeping g of x to be, whatever. It can be 0 or it cannot be. So if we do that, then again, we know that y prime is going to be just a derivative of y sub a and y sub b. Take the difference, and second derivatives kind of follow suit. We take all that information, plug it back into our original ODE. So this is y double prime here. This is y prime here. This is the new original function, meaning we're assuming now that the difference in between y sub a and y sub b will now be a solution. And so if we work everything out here, again, we get this situation here and here where we know, based upon what the definition of y sub a and y sub b are, that both of these have to equal g of x. Okay? And so since both this and that have to equal g of x, when we go plug everything in, we see that the only way that y sub a minus y sub b is going to be a solution to our second order linear non-homogeneous equation is that if g of x is 0. Okay? Now, I know it seems like we're kind of going in circles here because we know that, hey, if I have two functions that serve as a basis for the second order linear homogeneous equation, we know that that follows superposition, right? Well, it seems like we're kind of back to where we started. Well, yep, and we already know if we got two solutions that works like that, we know that the g of x is going to have to be 0. But the thing that is really special about what we've just done is we've actually done a little bit more than that, okay? So what we've actually have shown here is that if I have two particular solutions, excuse me, and they are distinct solutions to that particular differential equation, then we know that the difference of those two functions will actually act as a homogeneous solution, okay? So that means that if I take the difference of these two things, and I'm just going to use y sub h here, that's going to act like a homogeneous solution, meaning it's going to act like one of those functions that would actually be a part of a basis of a second order linear homogeneous equation, okay? Putting that another way, if I knew a function that was part of the basis of a second order linear homogeneous equation, what we're actually saying is that that homogeneous solution actually is coming from the difference of two other solutions that we haven't explicitly mentioned, okay? And so the key here is that if we actually knew what the two particular solutions, the y sub a and y sub b were, what we could actually do is we know that then the difference of these two particular solutions will actually be the same as a homogeneous solution, but more so, what we'd be able to do at that point, and this is the special thing, I would be able to express one of the particular solutions as a sum of the homogeneous solution plus the other particular solution, okay? And that is the thing that we needed to know, because that's going to explain why we say that y is equal to the homogeneous solution plus the particular solution. So what we've just discovered here is the key in us being able to find what a suitable solution would be, or the form of a suitable solution would be for a non-homogeneous linear equation, especially of second order here. So what we're going to do is do some renaming. So we're going to consider what we have here, and we're just going to do some renaming so that we can get it into this form here. So if we essentially let y sub a, let that just be y, and y sub b, let that be y sub p instead, p as in Paul, then of course if we relabel everything, then we see we have y minus y sub p equals y sub h. And this y sub h here is acting as the homogeneous solution, and this y sub p is acting as one of the two particular solutions that we would need to have for us to be able to solve this equation type. Okay, so now we've kind of gone through the process of showing why it is that we actually need the sum of the homogeneous solution plus particular solution to be able to come up with a suitable solution for a second order linear ordinary differential equation that is non-homogeneous. Okay. Now, the big question is, though, we know that we can easily find out what the homogeneous solutions are. How in the world are we going to find out what at least one of those particular solutions looks like? Okay. Especially when we're not given anything. Well, that is where the method of undetermined coefficients comes into play. And so this method is very straightforward, relatively speaking, but it's limited to only certain types of functions. And so I'm going to get more into why that is here in just a second. So let's kind of move forward here. So, of course, the goal here is to come up with a method to find what y sub p is. And so this is what we're going to talk about now. So the first thing that we want to do is, since we know that the total solution is just the sum of the homogeneous solution plus a particular solution, we're going to take the low-hanging fruit first, which is we are going to look at what the homogeneous solution is, go ahead and figure it out. Okay. The next thing that we'll do is we're going to make an educated guess on what the particular solution should look like in its general form. Now, to keep this short and sweet, what we are trying to do here is make sure or do a comparison in between what our homogeneous solution is going to be and what this function g of x is. Okay. And the main thing here is that we do not want any terms in our homogeneous solution in general to match any terms in our g of x function. Okay. In the case of 2a here, and I'm going to show you this chart that this is referring to here in just a second, but in the case where the homogeneous solution and the g of x function do not have any common terms in it. Okay, so let's say, for instance, if this had something like c1 plus e to the 3x minus plus c2 e raised to the minus 5x, something like that, then this case A here is talking about if my g of x had a function that looked nothing like this. So let's say g of x here was just x squared plus x. Okay, so we do not have any common terms in between these two. Okay, so I don't have any terms here that have a e to the 3x in it or e raised to the negative 5x in it, and I don't have any terms with just x squared in it or just x in it. So unlike terms here. If I have this situation here, then what I'm going to do is use the suggestion for what my y sub p function should be based upon this chart. And I'm going to go ahead and show you what this chart looks like now. So looking at this chart here, we know that if our g of x is just going to be some constant function, and here this is just an example of what that would look like, then we would just say that our y sub p in this case, well, y sub p here is just going to equal a, okay? If it's linear, if our g of x looks linear, and of course it's not matching any of the terms with the homogeneous solution, then of course we'll just let y sub p equal ax plus b, okay? Now, if we continue on here, you'll see for the quadratics, of course, it's going to be quadratic in nature. For the cubics, it's going to be cubic in nature. For the nth degree polynomial, that's just kind of taking it on, it's just going to be an nth degree polynomial. For sine and cosine functions, for either one of those, it would be a linear combination of a cosine function and a sine function. For just an exponential function, it'll just be some constant times that same exponential function. And so these last few are going to be combinations of the kind of functions that we've already seen. So if I have, let's say, a linear times an exponential, kind of like how you see here, then we'll do, the general form of a linear times that exponential, okay? We don't have to come here and say do a times c for the exponential part here as well, because if I go distribute the c, the both terms here, a times c is still just a constant, and b times c is still just a constant. So there's no point in doing that, because we're still just going to have the form of some constant times x plus another constant, all in parentheses, times e raised to the lambda x. So really no need to have a separate constant for the exponential part, okay? And thus, for the quadratic times exponential, it'll look very similar to what it does for linear. And here for the exponential and the sine, or exponential and the cosine function, that'll all look the same here. And of course, for these last two, I have the quadratic and sine, and of course I have these asterisks here because even though I'm saying sine, it could be sine or cosine, okay? And for this very last one here, even though I don't have it written in, so I'm going to write it in here, you see that we have this x times this exponential times this trig function. So really what this is an exponential times a linear times a sine, okay? And so we have all that in it. Now, if we did not have, let's say, the exponential part, then of course, let's say this would go away. Then that means that this part will go away, and then we would just have linear times sine. And of course, that means that would go away, and you would just have this, okay? So I kind of threw that catch-all all in there for the last one, just to kind of cover the exponential times linear times sine, as well as just a linear function times a sine or cosine function, okay? So the whole point for this chart, again, is to say, hey, for my initial guess on what my particular solution will be, of course, if my y sub h and my g, or g of x here, if we don't have any common terms in these two, I just take the suggestion for y sub p that I have here and I run with it, okay? So now back to our steps here for the method for finding our general solution for our non-homogeneous equation here. Again, if our homogeneous solution and g of x don't have any common terms, then we just, like I said before, we just take whatever the suggestion is and we run with it. Now, in the situation where we actually have a term or maybe more for the homogeneous solution and g of h matching, we're going to have to modify what our suggestion for y sub p is going to be, okay? And so I'm going to go over what that is and show you a myriad of examples as well, just so that you can get a good idea of what that actually looks like. But just know that if there's at least one term that is in common with our homogeneous solution and g of x, we're going to have to modify those terms to where that that matching of common terms is going to be in our general form of y sub p. And so after we are done doing that, we'll, of course, use systems of linear equations after taking that final suggestion that's actually going to work, finding the first and second derivatives for it, dumping it into our ODE and working everything out. We'll use systems of equations at that point to be able to figure out what the undetermined coefficients are. And so that's the reason for the name of the method called undetermined coefficients, because you're guessing what a general y sub p will end up being, and then you're finding out the specific coefficients for it. All right, so to get more specific with what these rules are that I'm talking about, that basic rule that went with that step A that I just showed you not too long ago, this is basically the step that says, hey, if y of h and g of x don't have any common terms with each other, just use y sub p as you know it, okay? If, again, we have some kind of matching, we have a term that matches in between a homogeneous solution and g, then what it's prescribed for us to do is to multiply our choice for a y sub p for that term or terms where a homogeneous solution and g are common. We need to multiply that by x raised to the m, where m is the smallest positive integer, to eliminate that duplication, okay? And so at the end of the day, we need to have no matching terms in between your y sub h and your y sub p whenever we start to work on everything, which means we don't need to have any matching terms in between your y sub h and your g of x either, okay? And so what I'm going to do after we go over this last rule is to show you examples of what that actually looks like. Now, of course, the sum rule is just saying, hey, just like in the chart I was showing you, if we have combinations of, let's say, a sine function and a quadratic function, then, of course, our general form for y sub p is just going to be the general form for a quadratic plus the general form for the combination of sine and cosine, okay? So the sum rule really isn't all that special. The modification rule is the one that's really important here. All right, so let's look at some examples of what all three of these rules actually looks like, meaning the basic rule, the modification rule, and the sum rule, so that we can get a good idea of how to judiciously pick good general solutions for our y sub p before we start solving these types of equations. So for our first example here, if we're just talking about the basic rule, then let's assume that our homogeneous solution is just c1 times e raised to the 3x plus c2 times e raised to the 4x. And let's assume for this time our g of x is just this quadratic function here, okay? Since we have no common terms that match in between the homogeneous solution and g of x here, we can just assume that our y sub p is going to be, in general, the form of a quadratic function, okay? Now, if we look at an example of what the modification rule looks like, again, we assume the same homogeneous solution, but now notice that our g of x function is now -5 times e raised to the -3x. And of course, this term is in common with the first term in our homogeneous solution. And so since these two terms are common, what I have to do is eliminate the duplication in between what I would have in between y sub h here, basically here and here. So I can't have a term here that just says a times e raised to the -3x, okay? Because that's basically going to get lumped up with this if I actually go through and do the first and second derivative and put it all into my ODE and try to solve for it. That's going to cause problems. So here, since this is the same as having C1 times e raised to the minus 3x times x raised to the 0, then of course, if I have x raised to the 1, that's going to be the smallest power of n here, power of x here, so that this and this term doesn't match, okay? And so that's how we take care of the duplication. Now, if we look at how the sum rule comes into play, I've actually done a modification plus a sum rule together, so you'll see what that looks like. Again, our homogeneous solution is the same, but now we see that our g of x is a combination of a quadratic expression, which is here, and an exponential expression, which is here. So for the quadratic expression, since we don't have any quadratic looking like terms in our homogeneous solution, we just write that portion of y sub p as is. Of course, for the second term here for our homogeneous solution, it matches, or it's common with this last term here for g of x. And again, because we don't want this term and this term to be alike, we need to add an x, x raised to the power that's 1 higher than what we have here for the homogeneous solution. And again, this is like x raised to the 0, so that means x raised to the 1 is going to be the next one up from that, and that's what we use, okay? All right, and so for the other example that I have from the modification rule, you see here that now our homogeneous solution has changed as well as our g of x has changed. So we're considering letting our homogeneous solution be c1 e raised to the 4x times c2 times x times e raised to the minus 3x. So now what we see is that, of course, we see that a homogeneous solution has a common term with g of x as far as the e raised to the 4x is concerned, okay? And we also see that our homogeneous solution here has this x times e raised to the minus 3x in it, okay? Now notice for g of x, it doesn't have a x times e raised to the minus 3x in it. So the problem is not going to be in between these two. The problem is going to be in the fact that our y sub p can't have any matching terms with our y sub h either, okay? So although this is different, we would still want to go the next power up on the x just to make sure that we don't have any issues, okay? And it's always okay to go higher. If you go higher, let's say if you go too high, then what you're just going to find out that in the process of solving, for your undetermined coefficients, you're just going to have some terms that fall out, basically. You're going to have something like 0 is equal to 0 for one of your equations, and that's fine. The problem is when you don't guess high enough, then that's when you start to see things break down in your whole process of trying to solve for the undetermined coefficients, okay? All right, so hopefully these examples here give you a good idea of what the method of undetermined coefficients is as far as getting us started in the equation solving process for a second order linear non-homogeneous equation. Everything else that we do afterwards, which I'm going to explain in the example videos, is pretty much using these guesses that we come up with here. So all these guesses that we did here. Of course, we'll have different problems, so our y sub p's will look different. But once we figure out what our y sub p is going to look like, it's pretty much you find what the first derivative is going to be, you find what the second derivative is going to be, and you put that stuff back into your original ODE, and then from there it's just algebra. And you're just really trying to figure out, let's say in this case, what your A, B, and C are. in this case, you're just trying to figure out what your A is. And it ends up just being systems of linear equations at that point. And again, we have several different methods for solving those types of systems. You can use whatever system or method you like, but as long as you can get the right answers, that's probably the important thing once you get to that point. All right, so this concludes part 1 of solving second order linear non-homogeneous equations. The next video that I'm going to do will be part 2 series, and in that series I am just going to go over examples. So I'll see you then.